Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Jannati binti Zahrin. Other members in this group are Nurul Jannah binti Muhammad Nur, Amin bin Anas and Jaslina binti Muhammad Sabrili. Today we would like to present our assignment for QFZ 3183 Modern Physics about leptons and hadrons, inelastic dispersion and quarks. The first principles of the universe are atoms and empty space. An atom consists of a central nucleus that is surrounded by one or more negatively charged electrons, and the nucleus is positively charged and contains one or more relatively heavy particles known as protons and neutrons. The total mass of atom, including the protons, neutrons, and electrons, is the atomic mass. The atomic mass is measured in atomic mass units, and atoms are made of leptons and quarks. Now I will explain briefly about hadrons and leptons. Hadrons are massive particles with internal structure that are made of quarks. Hadrons are classified into two, baryons and mesons. Baryons are specifically made of 3 quarks, but mesons are made of quark and antiquark. Examples of baryons are protons and neutrons. An example of mesons is pions that can either have charge or be neutral. Another family is leptons. Leptons are particles that are not made from smaller units of matter, so we call these as fundamental particles. Examples of leptons are electrons and muons, and this is quark composition for 2 baryons and mesons. Jaslina will explain about quarks in details.
Hi, I am Jaslina binti Muhammad Sabrili. Now we'll talk about the inelastic dispersion. Each scattering mechanism can be taken as independent of the others, since in the quantum mechanics, the scattering either occurs with full effect or it does not occur at all. Particles can be scattered from excitation in materials by several mechanisms, and one of them is inelastic. Let's go deeper about inelastic scattering or inelastic dispersion. Inelastic dispersion is the scattering process that generates heat because of the kinetic energy that is not being conserved. For example, in some photon studies, which is about the vibrational waves, a neutron loses energy when creating a photon, as we see in this diagram. So it is inelastic. Proton and neutron are no longer the fundamental particles. They are composed by quarks. What is quarks? So quark is the elementary particles. There are 6 types or 6 flavors of quarks that differ from one another in their mass and charge characteristic. As we can see, we have up quark, chum quark, top quark, down quark, strange quark, and bottom quark. Each of them have different mass with different charge. In quantum chromodynamic QCD, the colors red, green, and blue are ascribed to quarks, and the opposite anti-red, anti-green, and anti-blue are ascribed to anti-quarks. There are also gluons, which are also elementary particles. It transmits the forces that bind quarks together. As explained by QCD, gluons have the ability to create other gluons as they move between quarks. Thus, if a quark starts to speed away from its companions after being struck by an accelerated particle, the gluons utilize energy that they draw from the quark's motion to produce more gluons.
Now, let's talk about the latest finding of these elemental particles. On 20 December 2022, the International LHC collaboration at the Large Hadron Collider (LHC) presented new measurements of rare particle transformations or decay that provide one of the highest precision tests yet of a key property of the standard model of particle physics, known as lepton flavor universality. Previous study of this decay had hinted at intergrowing tension, with the theoretical prediction potentially due to the effect of new particles or forces. The result of the improved and wider-reaching analysis based on the full LHC dataset collected by the experiment during Run 1 and Run 2, which were presented at a seminar at CERN, that are in line with the standard model expectation. A central mystery of particle physics is why the 12 elementary quarks and leptons are arranged in pairs across 3 generations that are identical in all but mass, with ordinary matter comprising particles from the first lightest generation. Lepton flavor universality states that the fundamental forces are applying to the generation to which a lepton belongs. Interest in the flavor anomalies peaked in March 2021 when LHCb presented new results comparing the rates at which certain B-mesons composite particles that contain beauty quark decay into muons and electrons. According to the theory, decays involving muons and electrons should occur at the same rate once differences in the leptons masses are accounted for, but the LHCb results hinted that B-meson decay into muons at lower rate than predicted. The new LHCb analysis, which has been ongoing for the past 5 years, is more comprehensive. It considers two different B-meson decay modes simultaneously for the first time and provide better control of the background processes that can mimic the decays of B-mesons to electrons. In addition, the two decay modes are measured in two different mass regions, thus yielding 4 independent comparisons of decays. The results, which supersede previous comparisons, are in excellent agreement with the principle of lepton flavor universality. New dataset will allow LHCb to investigate lepton flavor universality further, in addition to conducting a wider research program that includes studies of new hadrons, including the search for exotic tetraquark and pentaquark, and investigation of the differences between matter and antimatter. An upgraded version of the experiment now in operation for LHC Run 3 will collect larger dataset that will allow even higher precision tests of rare particle decays. That such anomaly could potentially have been rare shows just how much remain unknown, since theoretical interpretation exposed a myriad of unanticipated possible phenomena.
Rare decays effect in new physics. Rare decays are a special class of flavor decays, where the standard model SM prediction is very small, and so new physics effect can have very large contribution. They are decays of the form of a beauty quark decaying to a strange or down quark and two leptons, and are mediated by penguin and box diagram in the standard model as shown in the Feynman diagrams. These Feynman diagrams are showing schematically how these rare decays proceed in the standard model. It is in these decays that the strongest hints of physics beyond the standard model have been seen. We have measured the angular distribution of the decay and found one of the angular distribution, P5, shows a deviation from the standard model prediction. This can be seen in this figure, where the black points are the measured value and the yellow boxes are a standard model prediction. This diagram shows measurement of one observable P5 from the angular analysis of the decay as a function of the mass of the muon system squared, along with a prediction from the standard model in yellow. Rare decays also allow tests of the assumption of lepton universality. The decays, differing only by lepton species, electron, muon, or tau, should be identical up to effect caused by their differing mass. For example, the decay beauty can be studied in both the muon and electron mode at LHCb.
These are the references that we use to complete this assignment. That's all from us. Thank you.